About how utterly weird things get at the quantum level.
Oh, absolutely. It challenges everything we think is common sense.
Totally. Like the double-slit experiment. It's the classic, isn't it? Particles acting like waves, being in multiple places. I mean, it's just wild.
It really is. And it's not just a quirky thought experiment either. The strangeness, the specific behavior, it's fundamental to how we understand matter and energy, like the basis of it all.
Right. And that's exactly what we're getting into today. We've gone through a whole stack of material, the basics of the double slit with light, then with electrons, digging into wave-particle duality, all that quantum weirdness.
Drawn from some really solid sources, too.
Yeah, places like Wikipedia, Physics World, Imperial News, UC Davis, Lumen Learning, Khan Academy, NIST, Britannica. It's a good range.
Taylor and Francis, NASA Science, University of Vermont, Share Tech Note as well. It gives a pretty comprehensive picture.
And it really makes you step back, doesn't it? This isn't just lab physics. It makes you question, well, what is reality, fundamentally?
Exactly. It pushes those boundaries.
So the question that's been sort of bouncing around in my head, and what we want to unpack, is about the double-slit experiment itself. We see the particles that go through the slits making that interference pattern, but what about all the ones that don't go through the slits?
Ah, that's a great question. Where do they go?
Yeah. Do they just, poof, disappear?
Yeah.
And what does that tell us about how matter and energy actually work?
It's a fantastic way in because it immediately bumps up against our everyday intuition, doesn't it? We think it goes through or it hits the wall. Simple.
Right, binary.
But the quantum world plays by different rules. It's more subtle.
Okay, so picture it. We're shooting, say, electrons at this barrier, the one with the two slits. We know the ones that make it through create that weird interference pattern on the detector screen behind it.
Yeah.
Bands of hits, then gaps, then hits.
Classic wave interference pattern, yeah.
But most of the barrier is solid, right? So
Yeah.
what happens to the electrons that just smack into the solid bits between or beside the slits? There must be loads of them.
There are. And thinking about it like a wave helps initially. Imagine a water wave hitting a barrier with a couple of openings. Not all the wave energy goes through the gaps, does it?
No, most of it hits the solid parts. It would reflect off or maybe just stop there.
Exactly. It interacts with the barrier.
Yeah.
Same idea fundamentally with our quantum waves. When the electron's probability wave encounters the solid material,
Yeah.
well, it interacts.
Interacts how? Like bouncing off.
That's one way. Reflection. Some electrons will scatter off the surface. The angle they hit at is the same angle they leave at, just like light off a mirror. That's elastic scattering.
Okay.
Another possibility is absorption. The electron hits the material, and its energy basically gets soaked up by the atoms in the barrier. It might wiggle them around a bit, create a tiny bit of heat. The electron effectively stops there.
So it becomes part of the barrier in a sense.
Its energy does, yeah. And crucially, only the part of the probability wave that actually reaches the openings, the slits, gets a chance to pass through. Transmission only happens at the slits.
Right. So if I fire one single electron, and its probability wave is mostly aimed at the solid bit, it just hits it. Like a tiny ball, it gets reflected or absorbed.
Pretty much.
And that electron then plays absolutely no part in building up that interference pattern we see on screen later.
None whatsoever. It's effectively removed from that part of the process. The interference pattern is only built by the electrons whose wave function actually propagated through one or both slits. Those are the only ones that contribute to the fringes.
Okay, but here's the really brain-breaking part for me. They've done this, sending electrons through one at a time, right? Like ping, wait a bit, ping.
Single electron sources.
And over time, you still get that interference pattern. How does one electron interfere with itself? There's nothing else there.
This is it. This is one of the absolute core mysteries and most profound results of quantum mechanics. The setup is just like you said. Fire them individually, detect them individually as dots on the screen.
Just dots.
Yeah.
Little particle impacts.
Little particle impacts. But as those dots accumulate, they don't just make two fuzzy bands behind the slits, which is what you'd expect if they were just little bullets.
No, they make the stripes. The interference pattern.
Exactly. The bright fringes where many electrons land, the dark fringes where almost none land. It's the unmistakable signature of wave interference.
It's like each electron somehow knows both slits are open, even if it, physically seems to only go through one. Or maybe.
Yeah.
Does it go through both?
That's the million-dollar question. The standard way to think about it is through the electron's inherent wave nature. Even a single electron isn't just a point particle traveling along. On its journey, it acts like a wave.
A wave of what?
A wave of probability. It's wave function. This wave spreads out, and it can encounter and pass through both slits simultaneously.
Hold on. The electron itself doesn't split in two, does it?
No, that's the key. It's detected as one whole electron, but the probability of where you'll find it behaves like a wave that went through both slits.
So the interference isn't electrons bumping into each other. It's the electron's own probability wave interfering with itself.
Precisely. Where the probability wave constructively interferes, peaks meeting peaks, you get a high probability of detection. That's a bright fringe.
And where destructively interferes, peaks meeting troughs, canceling out.
You get a low probability, a dark fringe. The wave function maps out the likelihood of finding the electron, and that likelihood shows interference.
Wow, okay. So thinking about all the electrons fired, do they all eventually hit something, like the back wall detector screen? Or can they just, get lost?
That's a really practical point. Does every electron fired contribute to something we can see? And the answer is, well, no, not necessarily the interference pattern on that main detector.
Okay, so where else could they end up? We talked about hitting the barrier itself.
Yeah, and that's the main one. Statistically, that barrier is mostly solid material compared to the tiny slits, so most electrons fired are probably going to hit the divider.
Just like throwing sand at a tiny hole in a big wall.
Exactly. Most hits the wall. Those electrons are reflected or absorbed. They don't reach the detector screen behind the slits. They're out.
Okay, that makes sense.
Yeah.
Any other ways they might go wall?
Well, even if an electron does pass through a slit, its journey isn't necessarily straightforward. There could be, stray gas molecules still in the vacuum chamber.
Even in a vacuum.
Yeah, vacuums are never perfect. An electron could collide with one and get scattered off in a random direction, missing the detector. It's usually minimized, but it's possible.
And what about the detector itself? Is it, like, a perfect catcher?
Modern detectors are incredibly good, very high efficiency. But nothing's 100% perfect.
Yeah.
There's always a minuscule chance an electron could zip through without triggering a detection. Very unlikely, but possible.
Okay.
And also, the detector screen isn't infinitely big, is it?
Right, it has edges.
So an electron could pass through a slit but get diffracted or scattered at such a wide angle that it just flies past the edge of the detector screen, lands somewhere else entirely.
So summing that up, most electrons probably hit the barrier and don't go through. A few that do go through might get scattered by stray atoms, or maybe miss the detector edge, or theoretically slip through undetected.
Correct. So the interference pattern we see is really built only from the subset of electrons that successfully navigated the slits and hit the active area of the detector and were detected.
Like we're only seeing the successful runs.
In a way, yes, the ones that complete that specific path and interaction sequence.
It really hammers home how different this is from, say, just shining a light waves or sending water waves at the barrier. If you did that, the parts of the wave hitting the barrier wouldn't just vanish from existence, would they?
No, definitely not. With a classical wave, the energy is continuous. The part hitting the barrier would reflect or be absorbed, maybe transmit slightly if the barrier wasn't perfectly opaque. You could, in principle, detect that reflected wave or the absorbed energy. The wave energy is conserved, it just goes different places.
But for the electrons hitting the barrier, it seems like their journey just stops there. As far as the interference is concerned, their interaction is very particle-like at that point.
That's a great way to put it. The interaction with the barrier seems to localize them, acting like particles. They don't then continue propagating as a wave through the barrier material to contribute to the pattern on the other side. Their wave nature aspect isn't relevant for that specific interaction.
Okay, let's tweak the experiment slightly in our minds. What if there's only one slit? Does a single particle showing its wave side still do something wave-like? Does it spread out, like diffract?
Yes, absolutely. Diffraction is a key wave phenomenon. If you have any wave passing through a narrow opening, it will spread out on the other side.
Like light through a keyhole making a fuzzy spot, not a sharp keyhole shape.
Exactly. You don't get a sharp shadow of the slit. You get a central bright band, which is brightest right behind the slit, fading outwards, possibly with dimmer fringes on either side. That's the diffraction pattern.
And if we fire electrons one by one through a single slit,
we see the same principle at play. Each electron hits the screen as a single localized dot, particle detection.
right?
But accumulate those dots over time, and what pattern do you get?
The diffraction pattern, the central fuzzy band.
Precisely. A diffraction pattern emerges. It confirms that even though detection is particle-like, The probability of where any single electron will land is governed by a wave that spread out diffracted as it passed through that single slit.
So both experiments, double-slit and single-slit, scream wave-particle duality, don't they?
They really do. You have particle nature clear as day at the source emission and at the detector, localized impact.
Hmm.
But the pattern of those impacts, whether it's interference from two slits or diffraction from one, can only be explained if the propagation between source and detector is governed by wave mechanics.
We deduce the wave part from the patterns,
Mm.
because interference and diffraction are just things waves do.
Exactly. That's the core of wave-particle duality. These quantum objects exhibit both kinds of properties. Which one you see depends on what you're measuring or how they're interacting.
Okay, this brings up another angle. Could it be that there is always a spread-out wave hitting the detector, but our detectors are just, I don't know, crude? They can only register it as a point particle.
That's a really clever thought, challenging the detection aspect, but the evidence we have strongly suggests that the interaction at the detector is genuinely localized, not just an artifact of measurement.
What evidence points that way?
Well, first, as we keep saying, the detections are point-like. A specific spot on the detector fires, not a whole area lighting up dimly. We get a click at one location.
Okay.
Second, the energy and momentum transfer is quantized. When, say, a photon hits a light detector, it delivers a specific chunk of energy related to its frequency. An electron delivers its specific charge and energy at one point. It's not like wave energy continuously washing over it. It's a discrete packet exchange, characteristic of a particle interaction.
And the pattern building up one dot at a time.
Exactly. If it were a continuous wave hitting the detector face, the whole pattern, faint at first, should appear all at once, reflecting the wave's intensity distribution. But it doesn't. It builds dot by dot by dot.
So the wave function really is more like a probability map, guiding where the particle is likely to show up when it does interact.
That's a very effective analogy, yeah. The wave function gives the probability amplitude. You square that amplitude, and you get the probability density, the likelihood of finding the particle at that location if you perform a measurement, like placing a detector there.
And when the particle is detected, it's suddenly there at that one spot.
Yeah.
That transition from spread out probability to definite location is that the infamous wave function collapse.
That's the term used in the standard or Copenhagen interpretation, yes. The idea is that before measurement, the system exists in a superposition of possibilities described by the wave function.
Like the electron having a probability being here or there or over there.
Exactly. Then, the act of measurement forces the system into one definite state. The wave function is said to instantaneously collapse from representing all possibilities to representing just the single measured outcome. The electron is now here.
From this cloud of maybe locations to one definite spot, just because we looked.
Well, looked, meaning interacted with a measurement device. But yes, that's the core idea of collapse. It's crucial to add, though, that this is probably the most debated part of quantum theory.
Right, because it sounds a bit magical, like consciousness is involved.
It raises all sorts of philosophical questions, and physicists have proposed alternative interpretations to avoid the seemingly abrupt collapse.
You mean like many worlds, where every possibility happens in a different universe?
That's one, yes. Many worlds suggest the wave function never collapses. Instead, the universe branches with each measurement, realizing all outcomes in different parallel worlds.
Whoa, okay. What else?
There's Bohmian mechanics, or pilot wave theory. It proposes that particles always have definite positions, but they're guided by a real quantum wave. So there's no collapse needed because the particle was always somewhere specific.
Hidden variables, kind of?
In a sense, yeah, though it's more complex than early hidden variable ideas. Then you have things like consistent histories, quantum Bayesianism, cubism, and crucially, decoherence theory.
Decoherence, what's that?
Decoherence explains how a quantum system interacts with its environment, like the detector, and loses its distinct quantum properties, its ability to show interference, its superposition very rapidly. It doesn't fully solve the measurement problem for everyone, but it explains how quantum possibilities effectively turn into classical probabilities for all practical purposes without necessarily invoking a fundamental collapse.
So the nature of measurement, that transition from quantum possibilities to the definite world we see, is still kind of fuzzy. Still being figured out.
It's definitely a frontier. There's no single, universally agreed upon interpretation. It's an active area of research, both theoretical and philosophical.
Wow. Okay. Well, this deep dive has certainly reinforced the sheer strangeness. The big takeaway for me remains this mind-bending wave-particle duality. Things acting like waves when they travel, influencing probabilities.
Spreading out, interfering, diffracting.
But then bam, they hit something, they get detected, and they're suddenly a localized particle again.
Exactly. And thinking about those electrons that don't make it through the slits, the ones hitting the barrier, that's important too. It reminds us it's all probabilistic.
Right, not every electron you fire is destined to participate in the cool quantum interference show.
Many just interact with the barrier in a more mundane, particle-like way, bounce off, get absorbed. It highlights that quantum mechanics deals in likelihoods, not certainties, for individual events.
So here's the thought I'm left chewing on. If that wave function is just describing probabilities, the chance of finding a particle somewhere, what does that say about where the particle is before we measure it?
The million-dollar question again.
Is it really smeared out? Is it in some limbo state? Or does our act of looking, of measuring, literally bring its specific location into reality? It makes you wonder about the nature of reality itself when we're not observing it, doesn't it?
It absolutely does. Does the moon exist only when you look at it? Quantum mechanics forces us to confront these incredibly deep questions about observation, reality, and the limits of our intuition. And the double-slit experiment is right there at the heart of it all, still posing profound challenges a century later.